Hi, my name is Manish Gupta, and in this video, I'm going to talk about scaling laws for dense retrieval. This is a very interesting topic, and this paper was accepted as the best paper at SIGA 2024. Okay, so let's get started. Now, you see there have been so many scaling laws. There are these two popular scaling laws in information retrieval. The first one is the Zipf's law, which basically says that the frequency of a word is inversely proportional to its rank, and the law is a power law. The curve that fits is the power law curve, right? There's also this Heap's law, which basically says, given a corpus, the number of distinct words is a power law function of the corpus size. Okay. Even in the NLP area, for large language models, people have sort of observed scaling laws in terms of the model performance as a function of model size, data volume, and computational capacity, right? But for dense retrieval, unfortunately, there have been no scaling laws studied so far. Dense retrieval is this way of doing retrieval, information retrieval, in the embedding space. So you take the query, you take the document, you encode them using some transformer-based encoder, and given a query, you basically try to figure out matching documents in the embedding space. In this particular setup, in which these authors studied the scaling laws for dense retrieval, they used a shared encoder for both queries and passages. From a dataset perspective, for training dense retrieval models, you basically need QRELs, which are query relevance judgments, given a set of documents, given a bunch of document corpus, right? So they study using two different document corpora. The first one is MS Marco passage ranking dataset, which is an English dataset with 8.8 million passages and 0.5 million queries. Second one is T2 ranking, which is a Chinese dataset with 300,000 queries and 2 million plus passages. They experiment with 24 BERT checkpoints as the shared encoder for queries and passages, with sizes from 0.5 million to 82 million. For the Chinese retrieval dataset, they experiment with the ERNIE series of models. You see, I mean, when you want to compute similarity between queries and passages, you could do single vector retrieval or multi-vector retrieval. Single vector basically means you use one vector for the queries and one vector for the documents to be as embeddings. They obtained that this paper focuses on single vector retrieval, and they basically use the CLS token as the representation for the query as well as for the document. Now, to train these models, you basically need positive labels between queries and documents, but we also need negative labels so that you can do contrastive training. And for that purpose, they basically obtain 256 random negative samples, as well as they basically use the in-batch negatives. For training, they use this contrastive ranking loss. So given a batch of samples with batch size B, the contrastive ranking loss is computed like this, which basically motivates higher similarity between query and the positive document versus lower similarity between query and the negative documents, 256 random negative documents, right? So they fine tune all their model checkpoints for 10,000 steps so as to have a fair comparison and come up with scaling laws in a more principled manner. Now, to evaluate the model performance for dense retrieval purposes, typically people use NDCG at K, map at K, those kinds of metrics. However, those metrics are not continuous. And therefore, they propose a new metric called as contrastive entropy, which is basically inspired by the contrastive ranking loss and the notion of perplexity that people typically use in the large language model world. Right. The contrastive entropy is defined in this manner. As you can see, the formula is super simple, super similar to the contrastive ranking loss. It motivates higher similarity between query and positive passages and lower similarity between query and the negative passages. Okay. So in fact, this contrastive entropy metric has been shown to be very highly correlated with standard metrics like MAP at 10 or NDCG at 10 and also recall at 10 in that senses. So here is contrastive entropy, here is MAP at 10, contrastive entropy versus NDCG at 10. And as you can observe, especially beyond contrastive entropy of about 0.2 or 0.25, this is literally a linear relationship between these two metrics. Since contrastive entropy is differentiable at all points, it is a very good thing to use, to optimize for and study scaling laws. Right? So how do the scaling laws look like? Right? So, I mean, the broad question is, how does the model size impact density retrieval performance? Are larger models better, or, and how better they are, right? So these two plots basically show for MS Markov passage ranking task and the T2 ranking task, right? Those two data sets. Y-axis contrastive entropy, x-axis model size in terms of non-embedding parameters. The red stars are basically the standard BERT series from BERT tiny to BERT base, and the blue ones are also BERT, but BERT variants, right? The black line is the fitted curve, and as you can observe, this is basically log scale on both sides. Log scale on both sides. So what you observe is that there is a power law relationship between the model size and the model performance, right? Clearly, the lower contrastive entropy is better, right? So lower is better. So higher models lead to lower contrastive entropy, and they follow a power law relationship, both for the MS Markov passage ranking dataset and T2 ranking dataset. For T2 ranking dataset, these red points are effectively the Ernie series checkpoints, essentially. Right? The other question is, how does annotated, the size of the annotated training dataset impact the density level performance? Again, these two plots are for MS Markov and T2 ranking. And you can observe that as the number of annotations increase, the contrastive entropy decreases, which basically means you get better performance, right? And they both follow a power law as well. Now, the other thing that they tried to study is how do different annotations, the quality of annotations impact the model performance. So model performance is measured here using cross entropy. And on the x-axis, we still have number of annotations, but there are various curves. The first curve is the human curve. So basically, these are human labeled query document relevant samples. There is a blue curve, green curve, and a yellow curve. Let's study, how those samples have been obtained. So they do this experimentation for MS Markov only. They obtain these labels using three different mechanisms besides the human labeling. These mechanisms are mentioned here: ChatGLM3, DocT5 query, and ICT. ICT is inverse closed task. Here, the query, here basically they take all the positive documents from the MS Markov dataset and they associate a query with those documents, which are basically just sentences from those passages themselves or from those documents themselves. So the idea is that you basically say that this query is positive for this document if that sentence is basically present in the document itself. Now, this is low quality labeled data for training purposes because, hey, I mean, the query exactly matches syntactically with what is mentioned in the document. And therefore, there's not much for the model to train here, right, and learn from. The second one is DocT5 query, which basically produces queries for each passage. You use this DocT5 model so as to essentially take the passage and produce relevant queries. ChatGLM3 is similar. You take the documents or passages and ask ChatGLM3 model, which is about a 7 billion parameter, 6 billion, 7 billion parameter model to generate queries. Okay. Now, you see, these two are basically semantically generated queries, and therefore they are better as data sets compared to ICT for training purposes. And that's what you observe in these curves. You observe that as the annotation data set size increases, your contrastive entropy drops, which is good because larger data leads to better model performance. However, you observe that the human performance is the best. The worst performance is from the ICT models because, well, these queries or these query document pairs are essentially very poor quality. They just syntactically match, but there's nothing for the model to semantically learn from. That's that. Now, but one other interesting thing to observe is that the DocT5 query is actually better in terms of performance compared to the ChatGLM3 model, which basically says that large language models still don't generate very interesting queries for these passages, for our BERT encoder model to learn from. Okay. Now, obviously, rather than studying, the impact of model size and the annotation data size separately on model performance, you could also study them together. And that is what is done here in this mixed scaling law plot. So the idea is that you vary the model size from BERT tiny to BERT base, and that's what these 5 curves stand for. And you also vary the number of number of training data samples. And you do observe a power law here as well. The power law is expressed in that form. So, it is basically a power law in terms of both the size of the annotated training data and the size of the model in terms of non-embedding parameters. Okay. Now, these scaling laws are good, but what is the practical implication of these laws? So practically, these scaling laws can actually help you in understanding how you should assign your budget, when you're training models for density purposes. Okay, so when you're trying to train these models, there are three costs to care for. One, data annotation cost. Yes, it is super expensive to get good quality annotated training data from humans, right? There's model training cost. Model training obviously involves back propagation, and that involves a whole bunch of floating point operations and so on. There's also model inference cost. So when you get a query, you basically do an encoder, inference pass. When you get a document, you do an encoder inference pass on the document, and then you basically come up with the response, right? Come up with the similarity scoring. So all of these costs are involved when using these models, training these models, inferring from these models for density purposes. Now, if you exclude the inference cost, the plot looks like what is shown in the right top. So it's predicted contrastive entropy, and there is number of non-embedding parameters. As model size increases, you expect the contrastive entropy to drop. So as you can observe from these curves are for different budget values. So if you have a budget of 5,000, the most optimal curve is to basically do this, right? Is to basically follow this curve, okay? Similarly, for a budget of 10,000, that's the curve to follow. For a budget of 150,000, that's the curve to follow, and so on. Okay. So yes, if you have smaller budgets, the best point. One thing to observe across these curves is that these curves indicate that as you increase the model size, the model performance becomes better and better. However, at a particular point, it starts to become worse. The contrastive entropy improves, which basically increases, which means the model performance starts to become worse. And that's the point where your data is limited. Remember, the data annotation cost is way larger compared to the model training cost. And therefore, for a particular size of model, certain amount of data is good. If you have less training data compared to that threshold size, the model performance just becomes worse. It's basically not a good idea to train larger models, if your budget is basically just $10,000. In fact, if your budget is just $20,000 approximately, it is best to train a 13 billion parameter model. If you do not care about the inference cost, that is. If you care about the inference costs are much higher, right? So if you care about the inference costs, this is how the curve looks like. Here, you can observe that, for very large budgets, essentially, because inference costs are crazy high, right? Even for very large budgets, you basically end up training just a few tens of millions of parameters size of model. Okay, so keeping inference costs in mind, people typically don't train very large models; they train very small models. But if you ignore the inference cost, then sure, I mean, for POC purposes, you could basically just train models like 13 billion parameter models with even a $20,000 budget. Okay. But more realistic scenarios, you do care about the inference cost as well, and therefore you would basically end up training a few tens of millions of parameters. Anyway, these scaling laws essentially help you nicely do budget allocation. That's basically the message. In summary, in this video, I talked about scaling laws for density retrieval using contrastive entropy as a metric. The authors observe power law relationship between model performance for density retrieval, and both model size and data size. Interestingly, LLMs still do not help generate relevant data annotations. Indeed, T5-based model was better in terms of generating relevant queries for documents to be used as training data for training density retrieval models. Scaling laws, as we observed, are important to do budget allocation management. That's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.